right, looks like we're working. Let's talk about waves. So this is 3.6 of chapter 3. Again, I haven't really shown this book yet, or that frequently, but this is the book we're going through, No Nonsense Quantum Field Theory. We are deep in chapter 3 now. We're on chapter 3.6. And we're going to be talking about waves today, right? So we're going to recap what it means to be a standing wave and what it means to be a wave with dispersion. So a standing wave, or just the wave equation. It's just, again, a part of me wants to go to the bare bones here, but another part of me wants to tell you just straight up what the wave equation is. If you don't know what it is, and if you don't know how it's derived, you can find that out other places. If you want me to talk about how the wave equation is derived, then I can do that in my Patreon. But I want to cut to the chase here because you guys are eager to learn about quantum fields, and if I go through every single derivation, every single practice thing, then it's going to take longer, right? These videos are going to be longer. I don't want them to be longer. I want to sort of break up these chapters in bite-sized chunks, and so that you can understand the material while also feeling like you're gaining headway, right? Because if I found, this is me going on a ramble a little bit, but I've found that when you go through books, it can get very monotonous at times. You can find yourself lost in the equations. Similarly, if you're going through those hour-and-a-half long lectures on YouTube about something that you're interested in, say topological quantum field theory or something like that, then it becomes at like the 30-minute mark, you're like, okay, maybe I should just give up on this, because it's just, the teacher makes it too boring. I can't focus. For any reason, you think to yourself, I'm just gonna go play guitar or something like that. And my goal is to sort of cut through all that jargon and give this to you straight up. And I feel like with some of the derivations, like the derivation of the wave equation, which I would love to do, I feel like that would just be cutting into some unnecessary time. And you guys would be just eager to get into the more nitty-gritty. You want to know what the point is, right? I hear this a lot in people that I've taught, students who always ask the question, they always ask the question, what's the point of all this? Right? And I feel like, again, this is me rambling. This is going to be maybe a shorter video because we're really just we're recapping on waves. But I feel like that question of what's the point of all of this, it's longing for cutting to the chase. And many times professors don't do that. They don't cut to the chase. They don't give you the punchline first. And I feel like sometimes if you're given the punchline first, then you can tell yourself, oh, okay, I know what's coming. And if I know what's coming, maybe I'll be able to retain this better. Maybe I'll be more invested. But if they just leave you at a cliffhanger all the time, then it's like, what's the point? But that's my spiel. Let's get into waves. So this is 3.6, a recap on waves. So the point of my spiel was to talk about waves, standing waves, just regular waves. So the wave equation, if you write down the wave equation, and then we're going to have a wave equation with dispersion. So our wave equation is going to be dt. So this is the partial derivative with respect to t, minus the speed of the wave times, and these are second derivatives, times the second derivative with respect to space. And this thing is going to be acting on some function, and it's a function of time and space. And that is equal to 0. That is the wave equation. The reason it's called the wave equation is because that phi, this function, is a wave, right? And we can verify for ourselves that this is a wave. Right? So the form of a wave can take, the most general form of a wave looks like this, e to the I argument. You put any argument in there, this is a wave, right? The reason this is a wave is because e to the I is a way, when you put I in the exponential of e, it turns an exponential into a wave. And the reason it does that is because you can go back, I think there's a Khan Academy video that covers why this is the case. It all has to do with Taylor expansions. If you Taylor expand cosine, and if you Taylor expand sine, then you multiply sine by I, then you get something that looks an awful lot like the Taylor expansion of e. So if we put that I in the exponential of e here, then you get to something called the Euler's famous formula, I think is what it's called. And Euler's famous formula is that e to the I, you put any argument here, x, is equal to cosine of x plus I sine of x. And we can do a lot with this, right? This is a huge, huge discovery in abstract math, because it relates exponentials with imaginary numbers with trig functions. So, and the use to us, my apologies, there's a bird behind me that's making a lot of noise. The most useful thing for us is going to be this e to the I argument. And we're going to make the argument be omega t minus kx, where this is, again, our temporal component. Right, so we have an angular momentum, and this is our spatial component of the wave. So temporal and spatial component of the wave. Oftentimes we write, I'll erase those, oftentimes we put a vector on k because, again, spatial component has x, y, and z components to it. And so we need, the k is fundamentally a vector that has x, y, and z components to it. So you can imagine, just imagine now, if this was phi, it's a function of t and x, a function of space and time, plugging that in to here, what do you get? Well, when you take the time derivative of phi, of this, twice, you're going to get negative omega squared times phi, right? Or to be a little bit more clear, we're going to get negative omega squared times e to the I omega t minus kx. So this is the time derivative of phi. I'll write that a little bit better. This is the second time derivative of phi of t of x. And similarly, the spatial component of phi of t of x. Again, I'm skipping through some steps. I'm assuming you've taken calculus also. And so if we do this one, then we're just focusing on the spatial components, right? We're bringing the exponential down. When we take the derivative, we're going to get a k squared because we're doing it twice. We're doing taking the derivative twice, and we're bringing that I down also because I is it's being multiplied by k, but we also have that minus sign. So what the minus sign essentially does is it just does this, right? It doesn't make it a minus, because I times I again is -1 times that negative right there. That's just positive. So that's e to the I omega t minus kx, right? So that's the second derivative with respect to sine, or with respect to the spatial components. So if we multiply that by c, because we have a c right here, we get that dt squared minus c squared dx squared of phi is equal to negative omega squared plus c squared k squared on phi, okay? And that has to equal 0, right? So that has to equal 0 because of this right here. So if that equals 0, we can divide both sides by phi, and we get minus omega squared plus c squared k squared equals 0. So minus omega squared equals minus c squared k squared. Omega equals square root of c squared k squared. So omega equals ck. So c equals omega over k. That was a lot, but a little bit of detail for you. So this is interesting. This is the velocity of the wave. So the velocity of the wave is equal to its angular momentum divided by its spatial momentum, or its spatial vector, the wave vector, k. I'll erase that. So let's take a look now at the wave equation with dispersion. So the wave equation with dispersion looks similar. So this is dt squared, the second derivative with respect to time, minus c squared dx squared plus m squared. Now, what does this do? Well, if we go back to this process, if we go back to this process here, we are going to see that when this acts on phi, this is going to be the same thing. Well, the time derivative again doesn't change. That's negative omega squared. C times the spatial derivative doesn't change either. So it's going to be plus c squared k squared. But then we have this m squared. Now there's no m in the exponential of our wave, right? So that'll just be multiplied by phi, right? Because we're going to get this m squared right here. By phi. Nothing's going to come down, right? It's just a number. right? When we operate on this function, I'm pointing this select. If we operate on this with m, it's just going to it's just going to be m times that, right? It's just going to be m times that. We're not going to bring anything down from the exponential. So what does this mean? If this is all equal to 0, then that means that omega minus omega squared plus c squared k squared plus m squared is equal to 0, right? Well, this is the same thing as c squared k squared plus m squared is equal to omega squared. So omega squared, actually we want to isolate c, we don't want to isolate we want to isolate c because we've isolated c right here, right? So let's see what c looks like. So this is going to be c squared k squared equals let's see, omega squared minus m squared. Oops. Make that squared look a little bit better. And then we're going to have that c squared is equal to k squared omega squared minus m squared. If omega squared is right here, it's right here, we're going to square that, right? We can say that this is c squared k squared minus m squared over k squared, and that equals c squared. So c is equal to the square root of c squared k squared minus m squared over k. This is a little bit different because we couldn't just, like we did for, like we did up here, we couldn't just take the square root and everything nicely boils down to this. If we take this, we just put it here, we find out that there's a k in the numerator and a k in the denominator, but we can't. This doesn't boil down nicely because of this minus m. And so, what that means is that we have to take a look at this again. There's no k in the numerator here, but there's a k here in the numerator. Again, what this means is that m is a huge factor in what determines the speed, right? And this, we could see that if k here decreases, we can't really infer what happens to the speed. Whereas if k here decreases, we can infer what happens to the speed. We see that the speed actually, if the k decreases, our denominator is decreasing, therefore speed is going to increase. And if here, we can't really tell because we have this minus m squared. And we could just put our omega squared again. That doesn't really change anything because, again, we need to know what m squared is. So the idea here is that the speed here, in this case, if we were to plot the speed as a function of k, if k decreases, then the speed is going to increase, right? Or if k increases, the speed is going to decrease. So if k increases, the speed is going to decrease. So we have some linear relationship. Here we don't. We don't have this linear relationship. So if k increases, it might increase to a point, but depending on what m is, it might begin to decrease. And this is what we call the wave width dispersion. This m factor is going to disperse this wave, if you will, because it messes with the velocity. And this is going to be important later on when we realize some things later in chapters, I think 7 or 6. I can't remember which one off the top of my head. But this is very important because, again, it's going to look something like this, as k can increase to a point, but only to a point to make it so that the speed also increases, but then it'll eventually decrease. So that's waves, right? So this is the 20-minute lowdown on waves. Waves with dispersion, waves without dispersion. And this is going to be extremely important later on. Again, I don't really like giving cliffhangers, but I don't want to, at the same time, I don't want to provide any confusions. So, and get too far ahead of myself. So that's waves with, again, dispersion and waves without dispersion. And I think we will call it there for right now. Again, if you have interest in supporting this channel, I have a Patreon page up. And if you want me to go over any other books, if you want me to go over anything in particular, then you can donate to this channel on my Patreon, and you'll be able to, depending on how much you want to support, I'll give you more priority or not, depending on how much you decide to support to this channel. So I will see you guys in the next one, where we'll be talking about gauge transformations, if I remember correctly, or gauge fields, right? So this one's going to be fun. This one's going to, this topic of gauge fields was a little bit difficult for me to get my head around when I was first starting to get into this stuff. But since I've had a couple of years to think about all of this, I feel like I'm in at least somewhat of a good standing to help you guys out on understanding this. So I will see you guys in the next one. Bye.